Hey, welcome back. So today we're going to be doing some exercises about vector components. Question 1 here says, let theta be the angle that the vector A makes with the x-axis, a positive x-axis measured counterclockwise from that axis, right? So find angle theta for a vector that has these components, and we're given 4 vectors here. I'm going to start out by drawing a set of axes here, just so I can do a quick little sketch of these 4 different vectors so I have some idea of what they kind of look like. This will help guide us as we answer these questions. Now what's important is that we have 4 different quadrants here defined by the x and y plane. This is going to be quadrant 1, this is going to be quadrant 2, this is going to be quadrant 3, and this will be quadrant 4. Okay, so let's sketch out these 4 vectors. So for vector A, we have A of x is 3, A of y is -2, so the tip of that vector will be there. Then B, and this is vector B would be around here. C is going to be around here, and D is going to be around there. So if I wanted now to draw these vectors, I could do them pretty simply, something like that, and like that, and that, and that. Okay, roughly speaking, right? Nothing too perfect. We've got 4 vectors here for these parts here, A, B, C, and D. Okay, now, how do we find this angle theta? Well, if you recall, we're going to be using, so if we define this as the angle theta to our part B vector here, A sub y is going to be this component right here, while A sub x is going to be this component right here. And we can see that tangent is going to be tangent of theta is going to be the opposite side over the adjacent. And so that's going to be A sub y over A sub x. And so we can write down a formula, and that formula is that theta is equal to the inverse tangent, or arctan, of A sub y over A sub x. And so this is the formula we're going to use to solve for theta on all 4 of these vectors. Okay, since I started drawing out things here with vector b, why don't I do this, solve it for vector b first. Okay, so theta is going to be the inverse tangent of A sub y, which is 2 meters, over A sub x, which is 3 meters, right? So the inverse tangent of 2/3. Let's bring out our calculator, and we'll get 2/3, and then we're going to take the inverse tangent of that. We get an angle of 33.7 degrees. 33.7 degrees. And does that look reasonable? Does this look like 33.7? Yeah, it does. That looks actually pretty reasonable. Okay, so good. Our formula is working. We're getting an answer here. Now let's look at vector A. Okay, so let's solve vector A next. We're going to use the same formula, right? The inverse tangent of A sub y is -2 and A sub x is 3. So in this case, it's very similar, but we have a negative sign in here, right? So it's going to be -0.66, and then we take the inverse tangent of that, and we get -33.7 degrees. Okay, so for A sub y to have an angle here of -33.7 degrees, it seems like we're going now clockwise, right? And then this would give us an angle here, theta, of 33.7 degrees clockwise, so in the negative direction. That makes sense. Okay, that could work. I see how we could accept that. So we could accept this as sort of our answer, just like we accept this one as our answer. But if we want to have this theta to be defined as we move from the positive clockwise, so counterclockwise, we want it to be a positive number. Then what we actually want is we want to define this angle, okay, as a positive number. How can we do that? Well, what we've done is we say we've moved this way, clockwise, 33.7 degrees. If we then add 360 degrees, it'll bring us back here and it will give us a positive number, right? So what we can do is we can correct this. I mean, it's not wrong, but we can translate it into a positive number by adding 360 degrees. And if we do that, add 360 degrees here, that's going to give us an angle of 326.3 degrees. And this is maybe a more standard way of writing down this angle as a positive number. Okay, so they're equivalent. Whichever way you prefer, they both work. Great. Okay, let's look at vector C right now. So C we're going to look at using the same formula. Inverse tangent of 2 meters over negative 3 meters. Okay, now if we look at this, we see that it's identical to the equation here that we solved for part A. And so we know we're going to get an angle here of negative 33.7 degrees. But obviously, that's not correct, right? Negative 33.7 degrees puts us here in quadrant 4, and we can see that vector C is in quadrant 2. So what went wrong? Well, what went wrong is that the function of tangent repeats itself every 180 degrees. So you could have an angle of negative 33.7 degrees, or you could be off by 180 degrees from that. And that's why we sketch this out, so we know what quadrant we should be in. So we know if we're off by 180. In this case, we are off by 180 degrees because tangent has repeated itself. We must then fix it by adding 180 degrees. So in this case, we're going to take 33.7 degrees, negative 33.7 degrees, and add 180 degrees. We get 146.3 degrees. Okay, so 146.3 degrees. Does that look like this angle here? Yes, it does, right? It's somewhere between 90 and 180. 146 seems like a reasonable answer. Okay, so we're learning to be wary when we do this inverse tangent operation. Check to see what quadrant your angle is in. You might be 180 degrees off. All right, finally, let's look at part D here using the same exact formula. The inverse tangent of, in this case, negative 2 meters over negative 3 meters, and that's going to be the same as this answer that we got here for part B, because the negatives will cancel out. And so we will get an answer of 33.7 degrees. And again, that's obviously incorrect because vector D is in quadrant 3. So what does that mean? It means we're off by 180. So we have to add 180 degrees to this, and that's going to give us 33.7 plus 180, 213.7 degrees. That is going to be our final answer for part D. And that makes sense, right? So the angle from here to here should be more than 180 and less than 270. So we're in the correct quadrant now that we've added that extra 180 degrees. All right, so this answers everything for question 1. Let's look at question 2. Okay, so for question 2 now, we have a little graphic here showing these 4 vectors, A, B, C, and D. And we want to use components of the 4 vectors to the right here to find the magnitude and direction of these vector sums. Now, if you recall, we used these same 4 vectors for our exercises in our previous lesson for exercises. So this should look familiar to you. Okay, the way I want to start out here is I want to start out by breaking all of these 4 vectors into their x and y components, and then we'll have them components ready and we can just sort of add and subtract them together to get the answers very quickly. So let me now create a table showing all the components for these vectors. Okay, so we're going to have different angle, we're going to have the actual vector sub the x component of the vector, and if you remember, the x component of a vector is going to be, so for example here, if this is theta, right? The x component will be here, and that's going to be the adjacent side. So it's going to be the adjacent side, so it's going to be v cosine theta. Likewise, the y component is going to be v of sine theta, as it's the opposite side to that angle, okay? All right, so this is what we have. Let me fill this in. Degrees. And over here, we're going to have 90 plus 20, so that's 110 degrees. And then over here, we're going to have 180 plus 20, so that's 200 degrees. All right. This is going to be equal to 200 meters and 0. All right, this is going to be equal to 125 times cosine of 45. This is going to be 125 times sine 45. This is going to be 300 meters times the cosine of 110. And this is going to be 300 meters times the sine of 110. And finally, this is going to be for d 190 meters times the cosine of 200 degrees. I guess I should label these, right? This is vector A, B, C, and D, right? And this is going to be 190 meters times the sine of 200 degrees. Okay, let me actually do the calculations here so we know what these values are. Okay, so we have the magnitudes for all of our components now. We should be able to go in and add these different vectors together. Let's do that. Okay, so for part A, we're looking for A plus vector B. So we're going to say that the resultant component in the x direction is equal to A sub x plus B sub x, right? And this is equal to, well, A sub x is 200 meters. And the B component, Bx, is equal to 88.4 meters, okay? Now the y component, so r sub y, is going to be A sub y plus B sub y. A sub y is 0, right? Because it's laying on the x-axis. That's 0 meters. Plus B sub y, which is 88.4. Okay. So what do we have here? 200 plus 88.4 is going to give us 288. And here we have 88.4. Okay, so this is the components for the resultant vector when we add these two together. But that's not what we need. We need to find the magnitude and the direction of that resultant vector. Okay, so let's look at this now. The magnitude of this resultant vector, we're going to be using Pythagorean theorem, right? A squared plus B squared equals C squared. In this case, C, the hypotenuse, is the resultant vector. So that's going to be equal to then A squared, which is 288 meters squared, plus B squared, which is 88.4 meters squared. And then we're going to take the square root of all of that, right? So let's do this calculation real fast. So we got 88.4. We square that. Okay, let's save that in our memory. And then we also have 288, and we square that, and we add that together. So our total is here, and then we're going to take the square root, and we get 301 meters. And this is our final magnitude for the resultant vectors, 301 meters, when adding vector A with vector B. Okay, good. So we got the magnitude, and now we need the direction. Well, we're going to be finding the direction the same way we did in question 1. We're going to be taking the inverse tangent of r sub y over r sub x, right? So this is going to be the inverse tangent of r sub y is 88.4, and then we have 288 for r sub x. So let's figure out what that is. We've got 88.4 over 288, and then we take the inverse tangent of that and we get 17.0 degrees, 17.0 degrees. And that kind of makes sense, right? So if we were to do this graphically and draw B over here, the resultant vector, yeah, the angle here would be about 17 degrees. So it's making sense, okay? We've got the angle, we've got the magnitude of the resultant vector, we're done. Okay, now we're going to do the same thing for the next couple of problems here. So for B, we're going to have r sub x and r sub y, right? So r sub x is equal to b sub x, which is 88.4, plus c sub x, which is going to be negative. So we're actually going to subtract 102 meters. And for r sub y, we're going to have b sub y, which is 88.4, and plus 282 meters. Okay, let's bring out our calculator real quick. So we've got 88.4 minus 102. So that's going to give us negative 13.6 meters. And then we also have 88.4 plus 282, 370 meters. Okay, so that's the resultant components. For the magnitude here, it's going to be using Pythagoras again. So we're going to have negative 13.6 meters squared plus 370 meters squared. And then we take the square root. And what do we get here? All right, 13.6 squared, technically negative, but that doesn't really make a difference. And then we also have 370 meters squared. We'll add that together, and total here, we take the square root of that, and we get 370 meters. And that's going to be our answer here. Now, what's interesting to notice is that the resultant vector calculation we got here for the total magnitude of the resultant vector is pretty much the same as the y component. And the reason why is because the y component here is very big. It's 370. And that x component, right, 370 in this direction. The x component is very small. It's only negative 13.6, right? So like right here. So the resultant vector is going to be almost vertical. And so the length difference from the y component is minimal. There is a small difference, but not within the level of our precision for the significant figures that we're using here. Okay, so let's take a look at theta as the inverse tangent of r sub y, which is 370 over negative 13.6. All right, let's do that. So we got 370 divided by 13.6, which is negative. And we'll take the inverse tangent and we get negative 87.9 degrees. Okay, now, is this reasonable? Negative 87.9 degrees is going to put us here in quadrant 4. This looks wrong, right? We're combining vectors b plus c. And we can see from our components, right? Our components here tell us that we should have a positive y and a negative x. So our resultant should be in quadrant 2. That means we're off by 180 degrees, okay? So we have to now add 180 degrees to get the correct answer here. This is where the sketch basically saves us. So we're going to add 180 degrees, and we're going to get an answer of 92.1 degrees. That is going to be the correct answer here for the angle in part B. All right, let's look at part C. Got r sub x and r sub y. So r sub x is going to be d minus a. Okay, so d sub x is negative 179 meters minus a. So that's minus 200 meters. And d sub y is going to be negative 65.0 meters. And a is going to be 0, so that's minus 0. So we see we get here negative 179 minus 200. That's minus 379. And here, this is just going to be negative 65.0 meters. So these are our components. So these are both negative, so we should be in quadrant 4. Oh, sorry, we should be in quadrant 3 when they're both negative. Okay, let's calculate the magnitude of this resultant now. That's going to be negative 37.9 meters squared plus negative 65 meters squared, and then we take the square root of that. Calculator time. 65. Oh, let me clear memory here. 65 squared. Put that in memory. And 37.9. Nope, that's not correct. 379. Okay, this should not sure why I have a decimal point there. Okay, let's try that again. So in memory, we still have the answer for 65 squared. So now we have 379 squared, and we add that to our memory, and then we're going to take the square root of all of that, and that's 385 meters. 385 meters. There we are. This is the length of our resultant vector. Let's calculate theta real quick. So that's going to be the inverse tangent of r sub y, negative 65 over negative 379. And so what do we get here? So the negatives cancel, 65 over 379. And we're going to take the inverse tangent, and we get 9.73 degrees. 9.73 degrees. That would put us in quadrant 1. But we can see our vector should be in quadrant 3 because we have negative for both the x and the y components. Okay, so our vector here should look something like that, our resultant. So we can tell we're off by 180 degrees again. So let's add 180 degrees, and this is going to equal 189 degrees. Or we can round it off, 190 degrees. Okay, so this is going to be our angle for part C. Okay, these were all fairly simple. Let's look at C plus D. Now, if you look at C plus D, you can do it the same exact way that we've done it so far. However, by taking a quick look at this drawing, we can see that since C is 20 degrees away from the y-axis and D is also 20 degrees away, we know that this is a right angle. Okay, so if we recognize that we have a right angle here, we can actually solve this problem in a slightly different way. You can imagine instead doing a vector addition of C plus D, doing a head to tail method, you'll get something like that. Let me draw that a little bit straighter. But you'll get something like that, right? So this will be our resultant vector here. This is going to be equal to we can use the magnitude to use Pythagoras to calculate the magnitude here. So it's just going to be a right triangle with two sides here, and the resultant is the hypotenuse. So instead of finding x and y components, we can just compute the magnitude directly, right? So the magnitude here of that resultant vector is going to be equal to 300 meters squared plus 190, right, D, 190 meters squared, and then take the square root of that. So we can find this directly. Let's do that. It's going to be 300 squared. Put that in memory. 190 squared. Add that together. And that's our total there. We take the square root, and that's going to be 355 meters for our total magnitude of the resultant. Okay, now how do we find theta? Well, we see that we want to find theta like this, right? This is our theta, but we can break this down into sections. So we can see that this section is 90 degrees, this section is 20, and so if we just add in this little bit here, let's call it phi, then we can add phi plus 20 plus 90 to get us our total theta, if that makes sense. Okay, so in this case, we're going to say that our angle theta is equal to that angle phi, right? We're just calling this angle here phi, plus 20 degrees away from the y-axis plus 90 degrees to get us to the positive x-axis. So in this case, we can calculate phi. Phi here is going to be, we can use tangent again, right? So we know the value of both of these, and so we can see that phi is going to be the inverse tangent of the opposite, which is 190, over the adjacent, which is 300 meters. Then we add 20 plus 90, and what do we get? So 190 divided by 300, and we're going to now take the inverse tangent of this to get phi. So phi is 32.3 degrees. Add 20, add 90, and our total answer is now 142 degrees. And that's going to be our answer right there for the angle of theta from the positive x-axis. Okay, finally, let's look at part E here. E is going to be 2b plus c minus d. All right. R sub x and R sub y. So for R sub x, we want 2 times b sub x, which is going to be 88.4. Plus c sub x, which is going to be negative 102, minus d, which is going to be plus 179 meters. And for our y, it's going to be 2 times b, which is 2 times 88.4, plus c sub y, which is going to be plus 282, and minus d, so this is going to be plus 65.0 meters. And we can just do the sum here with our calculator. So that's going to be 2 times 88.4 minus 102 plus 179, 254. Okay, so we've got 254 meters for our x component, and for our y component, it's 2 times 88.4 plus 282 plus 65, 524 meters for our y component. All right, so now we're going to just find the magnitude of this vector. So that's going to be 254 meters squared plus 524 meters squared, and we take the square root of that. And what does that give us? 254 squared, store that in memory, 524 squared, add that to memory, and that's the total. We'll take the square root, 582 meters. 582 meters is our total resultant vector length. And let's look now at the angle. It's going to be the inverse tangent of ry over rx. That's 524 over 254. So let us find what this is going to be. We have 524 divided by 254. Gives us our answer here. We take the inverse tangent of that, and we have an angle of 64.1 degrees, equals 64.1 degrees. Now, does this make sense? Okay, so both of these are positive, so we should be in the first quadrant, and 64.1 degrees is in the first quadrant, so we're good. we're done. Okay, we found the magnitude and the angle theta for adding 2b plus c minus d. Great. All right. Let's look at the last problem, question 3. Okay, for our final problem here, we have a delivery driver that drives 5.25 kilometers north, then 3.25 kilometers west, and then 2.5 kilometers south. We need to find the magnitude and direction of the resulting displacement using the method of components. Verify this answer agrees with a rough vector addition diagram. So we'll just check it afterwards with a graphic to see if it makes sense. Okay, so I want to start out by just sort of drawing out these vectors so I have some idea of what they look like. Okay, so we're saying there's a vector 5.25 kilometers north, and then there's another one, maybe 3.25 kilometers west, and then finally there's another shorter one, maybe not quite that short, 2.50 kilometers south. And we want to add them together using components. Let's call this vector A, let's call this one B, and let's call this one C. So what we want to find is a resultant vector, which is equal to A plus B plus C. Okay, so we can say that R sub x is going to be equal to A sub x plus B sub x plus C sub x, and same thing for y. R sub y will be A sub y plus B sub y plus C sub y. But this problem is actually pretty easy because all of these vectors lie parallel to the axes. So A sub x is going to be 0, right? B sub x is going to be negative 3.25 kilometers, and C sub x is going to be 0. So we've got our component here already for R sub x, and that's going to be negative 3.25 kilometers. Good, not too bad. In the y direction, A sub y is going to be positive 5.25 kilometers. B sub y is going to be 0, and C sub y is going to be negative 2.50 kilometers. And so now we can subtract these, and it's just going to be 5.25 minus 2.5, and that's going to be 2.75. 2.75 kilometers. Okay, so we've got our x and y components. So now the magnitude and direction should be fairly easy to compute, where the magnitude of r is going to be equal to, using Pythagorean theorem, negative 3.25 kilometers squared plus 2.75 kilometers squared, and then we take the square root of all of that. So let's do that real fast. 2.75, we're going to square that, save that amount, and then we have 3.25. We're going to square that, add that to our memory, and that's our total amount. We take the square root, and it's going to be 4.26, about 4.26 kilometers for the resultant vector. And finally, theta is going to be the inverse tangent of r sub y over r sub x, so 2.75, all over negative 3.25. So let's do this. We've got 2.75 divided by 3.25, but that's negative. And now we can take the inverse tangent and we get negative 40.2 degrees. Negative 40.2 degrees. Now, does this make sense? Okay, let's draw a quick sketch here. Right. What we see is we have a negative and a positive here. Okay, so our x component is going to be negative and our y component is going to be positive. So we should be in quadrant 2, but negative 40.2 degrees is going to put us in quadrant 4, which is wrong. So we must be off by 180 degrees. So to fix it, we're going to add 180 degrees, and that's going to be plus 180 degrees. Gives us 139.7 degrees. Let's just round it up and say it's 140 degrees. Okay, now 140 degrees is going to be in quadrant 2, right? More than 90, less than 180. Great. Okay, so this is our result. We have our magnitude and we have our direction. And we're going to now verify this using a rough sketch. Okay, so let me do a rough sketch of this here. And here's the idea. Let me draw vector A. So vector A is going to be, we said, about 5.25 kilometers this way. Let's say this is 5.2. And plus B, which is going to be 3.25 this way. So I'm going to roughly estimate it to be about here. Okay, it's it's shorter than A, but more than half. And finally C, which is going to be a little bit less than half of A. So I'll bring this down to, I don't know, about here. Okay, something like that. Now, what we can see is the resultant vector is going to look like, should look something like this, right? This is what our resultant vector should kind of look like. And we'll just call this our resultant vector right there. And does this make sense? Does this kind of agree with what we got here? Let's look at the magnitude. Okay, so magnitude should be 4.26. Does this look like 4.26? Yeah, kind of. I mean, it's bigger than C here, right? And it's smaller than A. Sorry, not C. It's bigger than B, and it's smaller than A. So that puts the magnitude about correct, right? So I like that. I like the length. And 140 degrees. Does that make sense? Yeah, it does. This kind of looks like 140, right? If we went all the way around, that'd be 180. 180 minus 40 degrees. Does this look like a 40-degree angle? It kind of does look like a 40-degree angle. So yeah, that works out as well. So our rough sketch here matches the numbers that we calculated, and I'm pretty happy with this answer. All right, so there we go. These are the answers to the questions. If you got them all right, congratulations. If you had a little bit of difficulty, I hope you see where maybe your error was. Still have any questions, let me know. Put them down in the comments below. Try and get to them and answer them for you. And look forward to seeing you in our next lesson when we continue learning about vectors and turning these components into true vectors. See you there. Bye-bye.